you'll hear a lot in digital logic. One is called the sum of product. So that's SOP. So when you're doing the homework, you might hear write the sum of product. They want you to write the answer using the sum of product. And the other one's called the product of sums. Product of sums. Now, what's the sum of product? That's when you have an expression written like this. Y equals A B bar C plus C A bar plus A bar B bar C bar. This is known as sum of product. Why? Because each one of these is what? A product, and what are you doing at the end? You're adding them. That's known as sum of product. If I was to build this, if I was to design this, I'll have what? 3 AND gates. This is the first one, A, B bar, and C. C and A bar. The hell are they making noises there? A bar, B bar, C bar. Notice AND gates, and at the end, what are you doing with them? You adding them together. That's an OR. That's what the design of that. Now the product of sums, listen to the name, product of sums. So you might look something like this. Y equals A bar plus B, ANDed with A plus B bar plus C bar, ANDed with B bar plus A bar. I'm just making things up. These are sums, and at the end, what are you going to do? Multiply them together. So your design, if you were to design that, I'm not worrying about the complement. This is A bar and B. That's an OR gate. This is A, B bar, C bar. A bar and B bar. And the design will look like this. So if they ask you to write the answer using sum of product, they want to see it like this. If they ask you to write the expression using product of sum, they want it to look like this. Notice here just quickly, I highlight a few things from the book, our book, in case people are wondering what the book we're using. It says, a standard sum term, also called max term, is a sum term that includes each variable. So we call this max term, bless you, we call this min terms. Each one of these is a max term. So when we're talking about the sum of product, you might hear me use the word max terms. This is min terms. It says here, a standard sum term. That's a sum term. I'm sorry, I was looking at the wrong one. A standard sum term, that's this one, that's a sum, is also known as a max term.
Which page are you on?
Page 46. That's called a max term. A standard sum term is called, that's a max term, that's a max term, that's a max term. These are min terms. So sum of product, we're talking about min terms. Because each one of these is a min term. Each one of these is a max terms. So if you hear something about max terms, they want you to write that as a sum. Now, sometimes the expression cannot be written as product of sum or sum product, or it might be both, actually. So it's not always going to be black and white. It's not going to be this or that. You end up with an expression, you go, oh, that's a min term, that's a product of sum, that's sum of product. So take this example. Let's say I have this example, x y bar plus y x bar. Well, obviously this is what? Product, and what are you doing after you multiply them? Sum them. So sum of product. Sum of product. Well, sometimes the expression looks like this. Q equals x plus y bar plus z, x bar plus z bar. Notice these are what? Product. The whole thing is called product of sums because you have sums here and you're adding them. What about if you have this? X plus y bar plus z, or x bar y z bar. Or what is this? Is that sum of product or product of sum? These actually belong to both of them. That's really, you can look at as product of sum or sum of product. It's not an and, because remember, this should have an and gate, then you OR them together. You go, well, I don't see an OR there. Well, you can OR it to 1. Or this one, an OR gate multiplied together. Well, this times what? 1. Or it was 0, not a 1 here. So this is really an OR gate and it multiplied by 1. So if you look at that, if you want to make it something, you go, well, it doesn't look like a product of sum or sum of product. I said, well, you can make that. If you multiply something by 1, does it change its value? What about that one? It's supposed to be a product of sum. Well, I can write that adding a 0 to something doesn't change. Now we have product and you sum them. So this belongs to both of them. You can't just say that's sum of product or product of sum. It could be either one. Right now it's addition. You go, oh, wait a minute, that's addition. Maybe that's a sum product. Maybe that's the product of sum. But these belong to both of them. There are some it doesn't belong to either one. If I leave it the way it is, without simplifying that, I'm not simplifying it. If I leave it the way it is, this is neither. It's not sum of product, because this is sum, but there's multiplication. That's a product here. So it's not sum of product, it's not a product of sum. So this is neither. But notice I can simplify that. I can use Boolean algebra. If I simplify it, I could make it one of these. How? Well, distribute that. So if you distribute that, what are you going to have? X bar y plus x, y, y. Now think about this. What's x and x bar in one gate? And. That's a 0. Because if one of them is 1, the other one is 0. If one of them is 0, the other one is 1. So you have an AND gate with one input 1, one input 0, and I don't care about the third one. Once you have a 0 in that AND gate, what happens? Gone. What is y and y? If you have an AND gate, just think of a y and y. That's a y. So if you simplify that, that's what you end up with. So if I was to design this before I simplify it, and again, I'm not counting the NOT gates, but if you want to count the NOT gates, that's what you have. You have a NOT gate for x. Take the result, OR it with y. Take the answer, AND it with what? Either one gate or another gate of x, y, like this. X, y, AND it with the result of this. With the new design, this is all you have. This will give me the same result as all of this. No need for an OR gate, no need for a NOT gate, no need for two of these gates. So I still have 3 on that chip that's available for me to use, because I'm only using 1. So let's take some of these, implement them, simplify them, see what they look like. Few of them here. I'm just going to the end of the book, trying to get some expressions. I don't know if we did this or not, but I think we did that example. There we go. The problem is you got to flip like 60 pages to get to the end of the book to find where the examples are. There we go. Let's take a few of them. And see if we can actually simplify them and come up with something. I got x bar, y bar, z bar, plus x bar, y bar, z, plus x bar, y, z, plus x, y bar, z, plus x, y, z. You have an expression that looks like this. And you want to simplify that expression using Boolean algebra. Now I'm looking at the first two here. If I look at the first two, I can factor out what? X bar, y bar. If I factor that out, what's left? Z bar plus z. What's z bar plus z? That's 1. Now, let's look at these two here. I like this one. What can we factor?
X and Z.
X and Z. What's left? Y bar plus Y. What's Y bar plus Y? X and Z. Now this one here. Well, watch this. I'm going to go add one more term to this. Can I just add a term? What's X plus X? X. So if you have X, you can write it twice. Well, I got this gate. I can write him twice. Why? Because now look at this and look at this. You can factor out what? YZ. If you take YZ, what's left? X bar plus X. What's X bar plus X? 1. And that's as far as I can go with it. So by writing that term, that one twice, and you could write any one of them twice, doesn't matter which one. But I notice this one is a nice one because that will simplify with this, that will simplify with that one. So if I have another set of these, I can work with this one and get that X bar out and shrink everything to 2 input AND gates. What about if you have a problem like this? Now, is this product of sum or sum of product, this one? Try again. How about neither? As of now, neither. If I multiply the z through it, yes. If I take the z and multiply it through, I'll have sum of product. But the way it's set up right now, it's neither. One of the Boolean Algebra, I don't know if I saved that paper last time or not. I meant when I was writing the rules on it, I meant to save it. I don't know if you have yours or not. And I wrote A bar B plus A. Right here. A plus A bar B. Can you see it? Where my finger is equal to A plus B. So that looks like one of the rules I have here. X bar Y. So this is what you have. You should be able to write that as X plus Y. This is one of the rules in the book. A plus A bar B is equal to A plus B. That's what I used. So I can take this and make it what? X plus Y. That will be what? Zx plus zy plus x bar y bar. Now this problem is what? Sum of products. We have all these multiplication, we adding them together, we have the sum of products. Again, let's try some Boolean algebra and see if I can simplify. let's say F equals A, B, C bar plus A, B bar, C plus A bar, B and C plus A, B and C. Now the fact each one of these, notice, has one there. Like if you look at this and this, you can simplify it, right? If I look at these two, the last one and this one, can you simplify it? Yes. If I look at the first one, the last one, can you simplify it? Yes. So you know what? If I have three of these, I'll be in good shape. I can do one with this, I can do one with this, I can do one with that one. Well, you can add it to itself 3 times or 2 more times. ABC plus ABC plus ABC is the same thing as ABC. And now I can grab the first and one of them. That's one group. Plus the second one, and ABC. Plus the last one. That allows me to group them into groups of 2's there. And each one I should be able to simplify. Here, AB, C bar plus C, which is 1. AC, B bar plus B, which is 1. And the last one, what? BC, A bar plus A, which is 1. And that's my answer. So just some examples for Boolean algebra, where we use them. Let me get back. There'll be plenty more. I'm not done with the Boolean algebra. What about the complement? So let's look at the complement. If you have an OR gate, and this is really fun stuff now, and you put a not over it, that becomes an OR. The result, it's A bar, B bar. And if you take an AND gate and you complement that, that becomes what? A bar plus B bar. These are known as DeMorgan's theorem. I don't know if the book, yep, it talks about them. Now those are powerful. And I'll explain to you why they are powerful in a minute there. Notice what this one's saying. If you have an OR gate, A and B, and now you complement that. The not means complement that. When you take an OR gate and complement it, what do you have? What's the name of the gate? NOR, not OR. Yes, NOR. So that's equivalent to an AND gate with both inputs being complemented. When you see that little circle, it means complement. This one says if you take an AND gate and you complement that, becomes an AND gate. That's equal to an OR gate with both inputs being complemented. Now, why am I interested in that? This could make my design much cheaper and much smaller. Let's say I'm in the lab and I'm building something, and this is my design. I won't put any knot just to make life easy. Let's say A, B, C, D. So this is A or B. This is C or D. My answer is what? A or B, ANDed with C plus D. That's what my answer is. If you were building this in the lab, you need 2 chips on that board. You need one for the OR and one for the AND. What I might suggest to you is, you know what? I want you to go to the lab and build this circuit, the same circuit, that above one. Build the above circuit. Using only NOR gates. I have a reason why I want to use NOR gates. Because instead of now 2 circuit boards on that board there, I can use 1. Just like an AND gate, just like an OR gate, you can have 1 chip that has 4 NOR gates on it, 2 inputs. How am I going to change these to NOR gates and change that to a NOR gate? Watch how simple and quick. I'm going to double complement. When you double complement something, does it change it? What's A not bar? Twice. That's A. So if you double complement something twice, it doesn't change it. Well, let me double complement this twice. Once here and once here. Once here and once here. By doing that, what happens to these 2 gates now? They're NOR gates, but what about that one? That's not a NOR. Or maybe it is. Let me bring that DeMorgan's theorem. It says an AND gate with both inputs being complemented in the front there is equal to what? A NOR gate. So this is really another NOR gate. So now my design will look like this. And notice again, instead of using 2 chips on that board, 1 for the ORs, 1 for the AND, I can use 1 chip and I still have 1 extra gate on it using NOR gates. That's because of DeMorgan's theorem. Any AND gates with both inputs going to it complement is equal to a NOR gates. Any OR gates with both inputs complement is equal to what? NAND gate. And I can do the reverse with that. If I have my design looks like this, I made one of them 3, one of them 2, one of them 2 here. I said build using only NAND gates. Again, I'm going to double complement everything. There's what my circuit looks like. So these two are NAND gates already. And what happens to an OR gate with both inputs complemented? DeMorgan's theorem said that's a NAND gate. So now my design, I'm only using a NAND gate. I didn't show you what will happen if one of the inputs is complemented, like A bar. And you still want to use only NAND gates. Can you make a NOT gate out of a NAND gate? Sure, you take the A and you feed it to both inputs of that NAND gate, and that's A NOT. Or if you have an OR gate and you want to get a NOT gate out of a NOR gate, so you can make a NOT gate out of them too. So if you have a lot of NOT gates and AND gates and NAND gates and OR gates, you can do the whole design using NAND or NOR with a little Boolean algebra and double complement there, and you can use only one or two type, two chips of the same type. Here's the problem. The book doesn't want to write these problems. When they ask you to simplify, they're not going to say simplify f equals this. So this is what they're going to tell you to simplify. So we have this expression. Can you simplify it? So you might see a problem like this. F of A, comma, B, comma, C. That tells me I'm using 3 variables. It is the summation of minterms of 1, 2, 3, 4, and 5. They're going to give you a problem like this and ask you to simplify. So when you see something like this, the summation of minterms, a minterm is what? Let me go back to my notes. Where is a minterm? We talk about the minterm and the max term. Where are you? Well, the minterm is just a term, one term. Where'd you go? Right here. Each one of these, when we say a minterm, it is actually eventually the sum of product. When that's what the summation means. Sum of minterms. Minterms is a product, an AND gate. So each one of these is a minterm. That's an AND gate. Each one of these is called a max term. So what you have is actually you have the one, let's look at that one. We have A, B, and C. And this is F. 0, 0, 0. That's location 0. This one tells you when this value is going to be a 1 because it is actually a sum of minterms, sum of AND, sum of product. The sum of product tells you when F is going to be 1. It says F will be 1, at 2, at 3, at 4, at 5. That's what that means. So this is 0, f is 0. 0, 0, 1, f is 1. 0, 1, 0, f is 1. That's a 2. 0, 1, 1, f is 1. 3. 0, 1, 1, 0, 0, that's the 4. That's a 4, f is 1. 1, 1, 0, 1, that's a 5, f is 1. 1, 1, 0, that's a 6, oh, that's a 0. And 1, 1, 1, that's a 7, f is 0. So when you see it written like this, the sum of minterms, a minterm is an and, a product.
Wait, how'd you get 6 and 7 for them?
Because you have 3 combinations. You have 8 different combinations, 3 variables. 2 to the power of 3 is 8. So I'm listing all the possible combinations that exist. So you have 8 of them from 0 to 7. You're only going to have a 1 on the ones they told you at 1, 2, 3, 4, and 5. That means you will have a 0 at 6, 0 at 7, 0 at 0. So the expression to have a value of 1 here, you got to write this as an AND gate, and you want to have a value of 1. How can this AND gate have a value of 1 when you have a 0 and 0? That means you got to have what? A complement, B complement, and C. When you have A complement, B complement, and C, when A is 0, complement that, that's what? 1. When B is 0, complement that, that's a 1. When C is 1, that's 1. 1 and 1 and 1 will give you what? A 1. This one, to have a 1, that means A has to be 0, B is 1, C is 0. For this one to be 1, A is 0, B and C, because they're both 1s. So if it's a 1, I leave it alone. If it's 0, I complement that. To get a 1 here, A is good, but B not and C not. And for this, A, B not, and C.
And you're considering all those possible combinations for AND gates only?
Well, any of them. You'll see that for any of them. So that tells you what F is. If you were to write F in expanded format, if you want to write that the long way, that would be what? A bar, B bar, C, plus A bar, B, C bar, plus A bar, B, C, plus A, B bar, C bar, plus A, B bar, C. That's what F will be. They just don't want to write all that stuff. They just put it in that format. It's the sum of these product. And for the answer to be 1, that means one of them has to be 1. Well, this guy will be 1 when A is 0, B is 0, and C is 1. Boom, got a 1. Now the question, how can I simplify this? So we have to go through the math and simplify that. Now I see, and I don't know if you see it, I see this one with this one. Can you see it? What do you notice they have in common? A bar and C, right? B bar plus B, which is 1. Let's see this one and this one. So the second one, what can you take out? Oh no. Did I do the wrong one? I did, I think. That's not it, right?
You can take C bar out.
Yeah, that one helped me because the other ones are backward. I highlighted the wrong one. I should took it with that one.
The last two terms. you
Yep,
can take
with
out
that one.
A,
Yep,
B bar.
you can factor A, B bar. So if I take that A, B bar, you get C bar plus C, which is 1. And what about this one? Well, let's leave it alone. A bar, B, C bar, right? Now, am I done? Probably not. Let's look at this. These two. I can factor an A out. What's left? C plus C bar B. And there is an identity for this. Remember that identity? A plus A bar B is equal to what? A plus B. I can use that here and make that what? C plus B. So if you distribute that, that's A bar C, A bar B, plus A B bar. So when you simplify that expression, you will have this one. But you're going to see them write the expression like this. They're not going to list all the combinations. It's too much work for them. They're not going to write this expression. Nobody wants to write them. You'll see me use that notation on the test all the time.
Wait, so that means that I don't, so F is equal to 1 at where?
At not x, at location, this value is 1,
Yeah.
this value is 2, when it's 3, when it's 4, when it's 5. Right there. I gave you that. So watch this. I'll make another one. I'll make it 4 variables. The summation of min. Once I say the summation, that's min terms. 5, 6, 9, 10, 14, and 15. That says when it's going to be on, when it's going to be 1. Now I'm using 4 variables. I can write the expression for it. So summation 5, 6, 9, 10, 11, 12. 5, 6, 9, 10, 14, and 15. Using 4 variable. What's a 5 in binary? 4 bits here. 5 is what? Isn't that 0, 1, 0, 1? That's a 5. A 6 is what? 0, 1, 1, 0. A 9 is a 9, 8, and 1? 1, 0, 0, 1. A 10, 8, and 2. 1, 0, 1, 0. 14, 8, 4 is 12, 2. And the 15, 1, 1, 1, 1. So you want A to be 0, right? So that's A naught, B, C naught, D. That's what the 5 is. I want A to be 0, B to be 1, C to be 0, D to be 1. This one, A naught, B, C, D naught. This one is what? A, B naught, C naught, and D. This one, A, B naught, C, D naught. This one, A, B, C, D naught. And the last one, A, B, C, and D. Does everyone see how we come up with these? And now you got to go through Boolean algebra and see if you can find anything that will simplify them.
So that's how the questions are going to be written out.
Most of them will be like this. Most of them. Some will give you the expression. I'll give you both at the beginning, just to practice. But eventually we're going to switch to that notation.
So middle two, right?
Well, I can see these two. The middle two, you said what? These two?
No, yeah, to the right.
These two?
I think so, right?
Nope.
No? Oh.
Notice D is different here.
Oh, all right.
C is different.
Yeah, something C, but,
Hmm?
okay. But I didn't see the D. Okay.
I can see these two here. That's it. The ones I can see. If you factor A, B, C out, what's left? D bar plus D, which is what? 1? I'm just copying the rest of the problem. Now, I see this and this. Can you see it? If you factor BC out, what's left in that one? A plus A bar, D bar. And we know this one will simplify to A plus D bar. That rule actually comes from A plus A bar B. It's A plus B. You go, well, that's a D bar. Well, you can let D bar be B. A plus A bar B. Let D bar equals B. You end up with that one. So if you simplify that, that's ABC plus BC D bar. Now bring the rest of the problem. So we're making progress. We're shrinking it. Did I leave? Yep, that's this one. So now I have to look again, see if anything else I can do. Oh, I see one. Look at this. And look at this. If you look at them, what do you notice? There's a C in them. Is that it? And the B bar, right? A D bar, I mean. If you factor that out, what's left there? B plus B bar A. That's like this, except backward. We're using A for B here and B for A. So this one can be written as B plus A. So if you multiply them, that's what? C, B, D bar plus A, C, D bar. Bring the rest of the problem. Oh, I see something else. You can see the problem start to fall apart. This one and this one. I'm looking for other ones to see if they work out.
What about the ABCs and the ACD bar? They're not
This one,
in the ACD bar.
AC, this one here,
Go over to
here.
the ABCD bar, and I'll do that.
Yep, we could actually. Oh, that's B and D, I'm sorry, that's the B and D, right? You can't.
Oh, it's a B and D.
Yep.
Okay, never mind.
So, I thought actually it does, but now you look at these two again, if you factor what? A and C out, you have B plus B bar, D bar, which simplify to what? B plus D bar. And if you do the math, it's A, C, B. Well, I like to put them in nice order. I don't like A, C, B. A, B, C plus A, C, D bar. Now let me bring the rest of it. And keep looking. Keep on looking, see if anything simplifies.
ACD bar, there's two that.
A, C, D bar. Which one? This one?
And the last one,
And which one?
middle one.
This one? Oh yes, that's the same thing, isn't it?
Yep.
So we can drop one of them out. That doesn't mean we're done. I'm sure there's other stuff we can factor. Let's see. That's D bar.
Yes.
It might be, I don't know, I'm just looking quickly, feeling the pressure of end of class there. But it looks like, I don't know if we're done with it or not, but I don't see quickly something common. It might be. But that's the process you have to go and keep looking. Can I simplify? What can I do with them? And at the end, hopefully, you'll find something that you can take out, and that's your final answer.
The only
The-
thing that I think might work would be ABC and ACD.
A, B, C here.
Yeah,
And which one?
the one to the right of it.
This
A
one?
and C are
Well, you can only pull what?
A and C.
A and C out. You can't really, this is B and D bar. Not much you can do with it. Can't add them. Two different variables. If I do this, I'll have what? A and D bar. And if I look at this and this, no, there's two things different. I can only factor a B out. Nope. If I look at this, I can, nope. Nothing here actually common. What about that one? The B, C, D bar.
This be the bars, you know.
Uh-oh. I just saw something here. Look at this. What can you factor out?
B.
Is it just B?
No, that's,
So what's left here? C, D bar, plus, that's in this one. What's left in this one?
A bar, C bar, D.
C bar D.
A bar,
C bar, D.
or C, D, I thought it was C, D bar. Man, nope, never mind. If that was C, D bar, I would be in good shape. Nope. It might be the last, that's the end of it. Yeah. Uh-oh. Doesn't want to erase now. I don't see anything, but I could be blind here. The point I'm trying to make here, a lot of us don't want to use Boolean algebra unless we have to. Because you got to spend hours before you can simplify a problem. You're going to see me do something else soon that will simplify that much quicker and easier. But not today. Not today. We'll do that maybe next class.